Here we will continue this EPA 608 Universal Certificate. Now this is the core of refrigeration cycle. This will core for study it will take 85 minutes. We will start step by step. Let's start with essential chemistry.
In this module, we will go over concepts in chemistry that will help you better understand how HVAC systems work.
Let's start.
An atom is the basic building block of all things. Everything around us can be broken down into their smallest unit of atoms. You can think of atoms as Lego blocks that can be arranged to form everything we see around us. Clusters of atoms are known as molecules. If atoms are Lego blocks, molecules would be a stack of Lego blocks in a particular quantity and order. For example, a water molecule, H2O, is made of 2 hydrogen atoms and 1 oxygen atom. This particular arrangement of 2 hydrogen atoms and 1 oxygen atom is what makes the molecule water. If we had 2 hydrogen atoms and 2 oxygen atoms, this molecule would no longer be water. It is the unique combination of atoms that makes the molecule what it is. Everything in the world is made of matter, from your TV, to the oceans, to the air you breathe. Matter is anything that has a volume and a mass. Matter is made up of atoms and molecules. Matter exists primarily in 3 states: solid, liquid, and vapor or gas. Note that gas and vapor refer to the same state of matter. For purposes of the EPA exam, we will refer to this state as just vapor.
In this video you are going to learn what the 3 states of matter are, some examples of each state of matter, the characteristic properties of the 3 states of matter. The 3 states of matter are solid, liquid and gas. Let us look at solids. An example of a solid is your computer. The properties of solids depend on how the particles in solids are packed. In a solid, the particles are closely packed in fixed positions and cannot move anywhere. So, solids are rigid, cannot be squashed or compressed, have a fixed shape and a fixed volume. They cannot flow. Now let us look at liquids. An example of a liquid is water. Just as with solids, the properties of liquids depend on how the particles in liquids are packed. In a liquid, the particles are again closely packed, but not as closely packed as in solids. So this means the particles in liquids can move around each other. So, liquids are not rigid, but because their particles are closely packed as in solids, they cannot be squashed or compressed. They do not have a fixed shape, but they do have a fixed volume. Beware with that one, as many students think because liquids do not have a fixed shape, they do not have a fixed volume either. But they are wrong. If someone orders a pint of beer, they cannot make it 2 pints by pouring it into different containers. As you know, liquids can flow. Finally, let us look at gases. An example of a gas is helium. This is the gas in party balloons, because it is less dense than air and unreactive. Again, as with solids and liquids, the properties of gases depend on how the particles in gases are packed. Unlike solids and liquids, the particles in gases are not closely packed, they are far apart. As a result, gases are not rigid and can be squashed or compressed. They do not have a fixed shape nor fixed volume. They fill the whole space they are in.
In today's video, we're going to look at the three states of matter: solid, liquid, and gas, and see how substances can change from one state to another. To do this, we're going to use a model called particle theory, which helps us explain how the particles in each state behave by considering each particle as a small, solid, inelastic sphere. In solids, there are strong forces of attraction between the particles, which holds them all close together in a fixed position to form a regular lattice structure. And because the particles are fixed, the overall substance keeps a definite shape and volume, so can't flow like a liquid. The particles can vibrate in their position though, so you can imagine them constantly jostling against each other. Now, if we heat up a solid, its particles gain more energy and start to vibrate even more, which weakens the forces between them. And at a certain temperature, which we call the melting point, the particles have enough energy to break free of their bonds, and the solid melts into a liquid. In liquids, there are only weak forces of attraction between the particles, so they're free to move around and are arranged pretty randomly. However, the weak forces of attraction do mean that the particles tend to stick together and are fairly compact. This means that liquids have a definite volume, even though their overall shape can change, and so flow to fit a container. If we then heat up our liquid, the particles will gain more energy, and this will make the particles move around faster, which weakens the forces holding the particles together. And once we reach the boiling point, the particles will have enough energy to break the bonds altogether, and so the liquid boils or evaporates into a gas. In gases, the force of attraction between the different particles is very weak, so they're basically free to move around by themselves. This means that gases don't keep a definite shape or volume, and instead will always fill a container as they spread out as much as possible. We normally say that gases are constantly moving with random motion, and this can be a bit confusing, because gas particles actually move in straight lines. They don't randomly swerve. What we actually mean by random motion is that particles can travel in any direction, and they'll end up being deflected by solid walls or other gas particles randomly. When we heat up a gas and the particles all get more energy and so travel faster, the gas will either expand if the container it's in is expandable, like a balloon, or if the container is fixed, then the pressure will just increase. On the other hand, if we cool the gas down enough, then the particles won't have enough energy to overcome the forces of attraction between them, and so bonds will start to form between the particles, condensing the gas into a liquid. Then, as we cool the liquid even further, the same thing happens. The particles won't have enough energy to overcome the attraction between them, and this time even more bonds form, fixing the particles in place and freezing the liquid into a solid.
The melting point is the temperature at which a solid changes to liquid. For example, the melting point of ice is normally 32 degrees Fahrenheit. This means that at any temperature below 32 degrees Fahrenheit, ice will stay solid. But if the surrounding temperature is 32 degrees Fahrenheit or higher, the ice will start to melt, changing state from solid to liquid. The boiling point is the temperature at which a liquid changes to gas. The boiling point of water is 212 degrees Fahrenheit or 100 degrees Celsius. This means that at any temperature below 212 degrees Fahrenheit, water remains liquid. For example, at a room temperature of 72 degrees Fahrenheit, a glass of water is just liquid. When we boil water, we notice that it stays liquid until it reaches 212 degrees Fahrenheit, which is when it starts bubbling. The bubbling is a sign that water is changing phase to gas. Note that 212 degrees Fahrenheit or 100 degrees Celsius is the temperature at which pure water starts to boil. If you measure the temperature at which water boils in your kitchen, you may see that the actual temperature is a little off. This is due to the minerals like calcium that are naturally dissolved in your water. We commonly think of temperature in terms of units like Fahrenheit or Celsius. Temperature is a measure of how fast the molecules in a substance are moving, on average. Temperature is a measure of how fast the molecules in a substance is moving, on average.
There are lots of different scales for measuring temperature. Fahrenheit and Celsius are the most commonly used in everyday life, but Fahrenheit is almost never used in science. The Celsius scale is based on the freezing point and boiling point of water. But even the Celsius scale isn't the best, because absolute zero on the Celsius scale is negative 273.15 degrees. The Kelvin scale is based on absolute zero and starts at 0 Kelvin with no negative numbers. 1 degree Celsius is equivalent to 1 degree Kelvin. Absolute zero is where the kinetic energy of atoms is zero, well, theoretically. It's easy to switch between Celsius and Kelvin. Just subtract 273.15 from Kelvin to get Celsius, or add 273.15 to Celsius to get Kelvin. For example, 20 degrees Celsius is 293.15 Kelvin. And make sure you don't say degrees Kelvin. It doesn't actually use degrees. It's just Kelvin. When particles of a gas are heated, the particles will speed up. This means that the kinetic energy of the particles has increased, and therefore the temperature of the gas has increased. But the reality is that not every particle is moving at the same speed. We'll start by viewing a scale that measures the relative number of particles at different speeds. Particles are always moving unless they're at absolute zero. These few particles with a slower speed have less kinetic energy, and these particles with faster speeds have higher kinetic energy. But we can't easily take a snapshot of just one or a few particles. When we measure the temperature, we're looking at the average kinetic energy of many particles. This bell curve may represent a fairly warm temperature, and this curve a relatively lower temperature. There are lots of particles that have the same kinetic energy at both of these temperatures, but again, temperature is the average kinetic energy of particles. If the temperature drops to absolute zero, the kinetic energy of the particles comes to a halt. This is where the Kelvin scale starts, which means that there are no negative numbers in Kelvin. It begins at zero, making it better than Celsius, but there's another reason that Kelvin is better than Celsius. It's better mathematically. If the temperature rises from 10 to 20 degrees Celsius, it appears to have doubled. But if you convert those numbers to Kelvin by adding 273, you'll see that the numbers haven't doubled at all. Kelvin is accurate when it comes to proportions, so use Kelvin in all of your chemistry calculations.
As the temperature inside the jar decreases, the water vapor molecules move more slowly. And as the temperature increases, the water vapor molecules move more quickly. Effects of temperature and pressure on matter. Both temperature and pressure has certain effects on states of matter. The kinetic theory of matter states that matter is composed of a large number of small particles that are in constant motion. The theory also explains the effect of pressure and temperature on states of matter. Temperature causes change in states of matter. As temperature increases, heat is absorbed in the form of energy. The kinetic energy of the molecules of a solid increases on absorption of heat, and they begin to vibrate with larger amplitude. When a fast-moving particle collides with a slower-moving particle, it transfers some of its energy to the slower-moving particle, thereby increasing the speed of the slow-moving particle. As high energy or high heat slowly diffuses across the material, the molecules of the solid break free the intermolecular forces. Gradually, there is a phase change from solid to liquid. The temperature at which a solid changes to liquid state at 1 atmosphere pressure is called its melting point. If heat is supplied further, the kinetic energy of the composite particles of the liquid increases and the molecules start to vibrate more energetically. When the molecules gain enough energy, they start escaping from the surface of the liquid by a process called evaporation. With an increase in temperature, the liquid starts to boil. The temperature at which a liquid boils at 1 atmosphere pressure is called boiling point. Thus, the kinetic theory of matter explains that with an increase in temperature, matter changes from solid to liquid to gas. Similarly, with a decrease in temperature, matter changes from its gaseous state to liquid and then gradually to its solid state. However, there are certain substances that change directly from solid to gas, or vice versa. This phenomenon is called sublimation. Example, camphor. Sublimation is the transition of a substance directly from its solid to gaseous phase, without passing through the intermediate liquid phase. During the phase change from solid to liquid and from liquid to gas, there is no temperature change, though heat is continuously absorbed. Latent heat is the energy released or absorbed by a body during a constant temperature process. Two of the more familiar forms of latent heat are latent heat of fusion and latent heat of vaporization. Latent heat of fusion is the energy change when a given substance is heated to change its state from solid to liquid. The temperature at which this occurs is the melting point. Latent heat of vaporization is the energy change required to transform a given quantity of a substance from liquid to gas at a given pressure.
We are all quite familiar with the concept of heat and can describe the sensation of feeling too hot or too cold. But understanding what things like heat and temperature really are on the molecular level can be pretty tricky business. Nevertheless, we must fundamentally understand them as a prerequisite to learning about thermodynamics. So let's dig into this abstract concept. We can start with temperature, like the temperature outside today. It might be hot, it might be cold, but in science, we want to quantify everything that we can. So saying something is hot or cold just isn't enough. We want to be able to say how hot or cold with numbers. But that begs the question, what is it that temperature is physically measuring? Temperature is measuring the amount of heat energy available for work in a system. And heat energy is related to the average kinetic energy of the atoms and molecules within that system. We know that greater kinetic energy means objects will move faster. And this is true of molecules in the atmosphere just as it is of macroscopic objects. So higher temperatures simply mean faster moving particles. This kinetic energy of motion is distributed amongst translational or side-to-side motion, rotational or spinning motion, and vibrational motion, where the covalent bonds in a molecule bend and stretch. Heat will flow from hot objects to cool objects because as the particles move, they will impart some of their kinetic energy onto other particles through collisions. This will continue to occur until the whole system is at the same temperature, in a state called thermal equilibrium. This is how thermometers measure temperature. Heat from the environment will be in contact with the thermometer and flow into the thermometer fluid, causing the atoms to gain kinetic energy, and the column will expand until it is in thermal equilibrium with the environment, thus allowing us to read the temperature in one of our man-made units. We must bear in mind that all phases of matter expand with higher temperature, whether solid, liquid, or gas. This phenomenon is called thermal expansion. Energy is transferred as heat in a wide variety of processes. When a collision occurs, there is usually some heat generated. Friction can cause heat as well, which is why your hands warm up when you rub them together vigorously. In each case, we are considering the kinetic energy of the particles and the transfer of some of this energy to other particles as the definitions of heat and heat transfer. Heat is therefore a kind of energy in transit and will be measured in joules just like any other kind of energy. Furthermore, the transfer of heat energy will always alter the temperature of an object, as heat will always flow from the higher temperature object to the lower temperature object until thermal equilibrium is reached. This is why hot objects feel hot and cold objects feel cold, because a hot cup of coffee, which is hotter than your hand, will transfer heat into your hand, while a cold piece of ice, which is colder than your hand, will cause heat to be transferred out of your hand and into the ice. These events produce the hot and cold sensations we feel in our day-to-day lives. Now that we better understand heat and temperature, let's check comprehension.
Pressure is defined as the force exerted over a certain area. Applying pressure on matter can change their properties, including their temperature.
In today's video, we're going to cover the concept of pressure. We can define pressure as the force per unit of area, and we can quantify it using this formula, which says that pressure, measured in pascals, is equal to force divided by area. So if you hit a nail with a hammer, you would be applying a force to the area of the nail head, which would result in a pressure on the nail. For example, if you applied 800 newtons of force and the area of the nail head was 0.0001 meters squared, then you'll generate a pressure of 8 million pascals, or 8,000 kilopascals. In this case, the pressure was created from the collision of two solid objects, the hammer and the nail. In the case of fluids though, which includes both liquids and gases, the particles that they're made of constantly bang into their surroundings and generate pressure. For example, if we had a container of gas, the collisions of the gas particles with the wall would create pressure, because each collision applies a force to the inside area of the container. The same thing happens with liquids. For example, if we had a beaker of water, it would apply forces outwards in all directions, as the water particles collide with the glass walls on the sides and bottom, and with the air at the surface. So this would again create pressure. We refer to these two types, in gases and liquids, as fluid pressure. If you think about the Earth's atmosphere, it's basically a thin layer of gases that surrounds our entire planet, made up mostly of nitrogen, but also with a fair bit of oxygen, which allows us to breathe. It also contains the greenhouse gases that keep the planet warm, and the ozone layer, which keeps out the most harmful radiation. Importantly though, the density of the gas particles is highest near the Earth's surface, and the pressure then gets smaller and smaller the further away from the Earth you get. In this video, we're looking at atmospheric pressure, and this idea of the density decreasing as you get further and further away from the Earth is one of the main reasons why atmospheric pressure also decreases the higher up you go. We can see this if we plot a graph of atmospheric pressure against elevation above sea level. If we compare an object at sea level to the same object at 1,000 meters up in the air, then there's going to be a lot more air particles around the object which is at sea level. And this means that there'll be a lot more collisions with the surface of this sea level object than there would the object which is really high up. And if there's more collisions, there's also going to be a greater force overall, which if we look at our pressure equation, we can tell will create a higher pressure, because a bigger force means a bigger pressure. So in summary, because there's a lot more particles closer to the Earth, any object that's closer to the Earth is going to feel much more pressure, because all those particles are going to be constantly colliding with it.
The effect of pressure is negligible on solids, more on liquids, and the most on gases. When pressure is applied on a container of gas, the gas particles come closer to each other. This reduces the kinetic energy of the particles. When pressure is increased further, the gas particles come very close to each other and consequently get converted to liquid. Change in pressure also causes change in the temperature at which a material transforms from one state to another. So, if pressure is greater, higher temperature is needed to change the state of the material. By increasing the pressure, carbon dioxide can be changed to solid. Solid carbon dioxide is known as dry ice. By increasing the pressure and decreasing the temperature, Air can also be liquefied. The pressure of air particles present in the atmosphere is called atmospheric pressure. The different units of pressure are Pascal, bar and torr. Pressure also affects the melting point of substances. Most substances expand when they melt. An increase of pressure delays the melting of these substances. In some substances, the melting point increases with an increase in pressure.
So you can actually cause the phase behavior of a material to change by changing a pressure. Now, what is pressure? So pressure, of course, is the effect of the gas that is around us that is squeezing on ourselves all the time. So we get so used to it we don't even feel it, but actually the pressure of the air around us is pretty high. It's called 1 atmosphere of pressure, and it's essentially a force that's squeezing on us all the time, that our bodies are squeezing out at. Now, you know from either experience or not that if you climb a very high mountain, the amount of air that is around you decreases. So let me show you what the phase behavior of water looks like as a function of pressure. So here's the phase diagram that I showed you before. At 0 degrees Celsius, water transitions from a liquid to a solid, and at 100 degrees Celsius, water transitions from a liquid to a gas. If we increase the pressure to about 1.5 atmospheres, then it turns out that the solid-liquid transition still occurs at around 0 degrees Celsius. It doesn't change very much, but the liquid-gas transition occurs at a higher temperature. It's at about 112 degrees Celsius. Whereas in turn, if we lower the pressure, so if we went down to about, say, 3/4 of an atmosphere, then again the liquid-solid temperature stays about the same, but the liquid-gas transition temperature decreases to about 92 degrees Celsius. Scientists like to organize this in what we call a two-dimensional phase diagram. So this is a phase diagram where on the x-axis we have the temperature, and on the y-axis we have the pressure. And what we do is we label the locus of points where the material changes from a solid to a liquid to a gas by simply connecting the dots of the lines that we've just drawn before. And this is something that we call a phase diagram. So this is a two-dimensional phase diagram, and you see in this phase diagram that there is a region, there's a big region where the material is a solid, there's another region where the material is a liquid, and there's a third region where the material is a gas. At any point that you are on the phase diagram, so you can always find out what the behavior of the material is. So, at 1 atmosphere and about 23 degrees Celsius, you can read off this plot that water is a liquid. But this allows you to generalize it to many other conditions. And so nitrogen has a phase diagram that you'll see looks a lot like that of water, and there's a solid phase, a liquid phase, and a gas phase. At low enough pressures, actually, nitrogen also has a situation where the solid phase transitions directly to a gas without a liquid phase, but there's this big liquid phase, which is the part at 1 atmosphere that gives rise to liquid nitrogen.
If we change the pressure, we can change the phase of the liquid nitrogen by cooling it. I'm going to use this vacuum system, and as it evaporates, the heat goes off with the gas, and the liquid that's left behind gets colder and colder. And at some point, we're going to get below the melting temperature of nitrogen, and hopefully we will see solid nitrogen. And I'm going to do this. First, I'm going to turn on the pump, and then quickly. So the nitrogen is boiling now because the pressure over it is lower than its vapor pressure. It's internal heat that's causing it to boil. It boils, it cools, and then what we see is solid nitrogen. Here is dry ice. If we raise the pressure, we can put the dry ice, we can put the carbon dioxide in a place where it can exist as a liquid. Going to seal it up so that the gas cannot escape. Because the gas can't escape, the pressure inside of the tube is going to go up. When the pressure inside of the tube reaches about 5 atmospheres, the dry ice reaches a point where instead of going directly to gas, subliming, it can melt. It can turn from a solid to a liquid. Now what's going on right now is heat going into the tube is causing the dry ice to sublime. As the gas builds up inside of the tube, the pressure goes up. And as the pressure goes up, there it goes, the dry ice now can melt. Now we have mostly liquid, and if I release the pressure, the liquid carbon dioxide can no longer exist as a liquid. And because it's still cold, it condenses straight back into a solid.
So back to boiling. Boiling happens when water molecules have enough energy to spread out and to form bubbles. These bubbles rise to the surface and they release the water vapor. Since the water vapor contains these more energetic molecules, releasing them into the air cools the water. So here we have our beaker with a bubble. If we increase the pressure, the molecules in the bubble will move closer together and eventually they'll change back into liquid water. Alternatively, if we decrease the pressure, that makes it easier for those water molecules to spread out and form a bubble, and that's boiling. We can see this with the syringe. We push in the plunger, we increase the pressure, molecules move closer together and the bubble becomes smaller. When we pull the plunger out, we're decreasing the pressure. That means those molecules can spread out more easily and the bubble grows. If we pull the plunger out and decrease the pressure enough, water will start boiling. Note that the temperature doesn't change. It doesn't get hotter when it boils. It's just that there's low pressure, the molecules can spread out to form bubbles, and that's what we see happening here. Boiling is strongly influenced by the atmospheric pressure. On Earth, that pressure is created by gravity pulling air molecules down towards Earth. Those air molecules push on a liquid and they can make it more difficult for boiling to take place. Remove the pressure, and it's easier for boiling to take place as the more energetic molecules spread out and form bubbles. Note that we haven't talked about the pressure created by molecules of water escaping.
I'm going to try to demonstrate something called regelation, which is where you provide a pressure onto ice and that turns it into water, but after that pressure is removed, it freezes again. So in order to demonstrate this, I've taken apart the high E string from my guitar. I chose the E string because it's thinner than a G string, and that's important. And I've weighted it with these 2 bottles of water. When I apply the string across the ice, we should see the wire start to cut through the ice and perform the regelation of the ice. Well, we'll see if it works because we are outside in Sydney and it's warmer than 0 degrees, obviously. Alright, it's past 3 a.m., but the experiment has been a success. I passed this wire through this giant block of ice, and it's still a solid block. You can actually see the point where the wire went through here. So we pretty clearly demonstrated regelation, the idea that you can compress the ice, turn it into water, and then when that pressure is gone, it solidifies again as ice. Pretty cool stuff.
From the previous videos, we see that as pressure increases, a substance's boiling point increases. Conversely, we see that as pressure decreases, a substance's boiling point decreases. Matter exists primarily in three states: solid, liquid, and gas. When temperature is increased or decreased, a substance changes state. This occurs at the melting or boiling point. When pressure is increased, a substance's boiling point increases. Understanding these essential concepts will allow us to better understand the refrigeration cycle.
Yeah, so this essential chemistry. Let's go to the next one. Okay, this physical states of matter.
In this module, we will go over the physical concepts that are the foundation of how refrigeration equipment works.
From our essential chemistry module, we saw that there are three primary states of matter: solid, liquid, and vapor, gas. The state that a substance is in depends on both its temperature and pressure. If we change the pressure, temperature, or both, we can change the state of the substance. For example, an ice cube is in solid form. If you were to put an ice cube in a pan and heat it up, its temperature will increase until it becomes a puddle of water. It is then in liquid form. As you continue to heat up the water, it will increase in temperature until it bubbles up and becomes steam. This is water vapor. We can also change the state of a substance by applying or removing pressure.
Boiling. Boiling happens when water molecules have enough energy to spread out and to form bubbles. These bubbles rise to the surface and they release the water vapor. Since the water vapor contains these more energetic molecules, releasing them into the air cools the water. We have our beaker. If we increase the pressure, molecules in the bubble, and eventually they'll change back into liquid water. Alternatively, if we decrease the pressure, that makes it easier for those water molecules to spread out and form a bubble, and that's boiling. We can see this with the syringe. We push in the plunger, we increase the pressure, molecules move closer together, and the bubble becomes smaller. When we pull the plunger out, we're decreasing the pressure. That means those molecules can spread out more easily, and the bubble grows. If we pull the plunger out and decrease the pressure enough, water will start boiling.
As mentioned in the video, increasing the pressure acting on a bubble changes the vapor to liquid. Decreasing the pressure acting on the bubble changes liquid to vapor.
As the temperature of a liquid increases, what phase does it turn it into? Assume constant pressure. Okay, so liquid temperature, liquid increases, it will convert to vapor. Yeah, that's correct. Which of the following states has the highest temperature? Assume constant pressure. The highest temperature is solid, liquid, vapor, water, vapor. I think is the highest temperature. Yeah. If we increase the pressure acting on liquid, what state can be substantiated to? Okay, we are increasing now pressure. Okay, in a constant temperature acting on liquid, it will convert to solid.
So as we add heat to water, the water molecules begin moving faster, and some of them spread out and form a gas. We call that gas water vapor, and that's what's inside the bubbles you see. These bubbles rise to the surface, and this is what we call boiling. So we'll start with the water molecule. The red is oxygen, and the two white atoms are hydrogen. That's H2O. Water molecules are always moving. When we add heat, they move faster. And if we add enough heat, they'll spread out and they'll form a gas. We call that gas water vapor. Note that there's nothing between the atoms here. The black is empty space. To understand why bubbles form during boiling, imagine a group of water molecules, and as you add heat, some of them spread out and form a gas, water vapor. When they spread out, they push the molecules around them away, and that forms the bubble that you see. That bubble rises to the surface. That's boiling. Remember, there are only water molecules in those bubbles. They're very energetic water molecules in the form of a gas, which we call water vapor.
Temperature is a measure of how fast the molecules are moving in a substance, on average. The higher the temperature, the faster the molecules are moving inside the substance. In the refrigeration cycle, the process of changing from a liquid to a vapor is called boiling or vaporization. Note that you need to add heat to a substance for it to change state from liquid to vapor. As we learned from the Essential Chemistry module, there are bonds between water molecules that hold them together, allowing them to form a single mass of water. When we add heat, we increase the temperature and make the molecules move faster until they overcome the bonds between them. At this point, the water begins to vaporize or turn into steam. This is what is happening when we see steam coming up from a pot.
Boiling requires the addition of heat. True. For the same substance, the average speed of molecules in its vapor is faster than the average speed of molecule in its liquid on the same substance. Yeah, I think this is
Boiling
true.
or vaporization occurs at a
Yeah.
temperature called the boiling point. Each substance has its unique boiling point depending on its physical properties. The boiling point of pure water, for example, is 212 degrees Fahrenheit or 100 degrees Celsius. That's the temperature where water becomes vapor at a pressure of 1 atmosphere, which is the standard pressure of the air around us at sea level. The boiling point of any given liquid depends on pressure. At a higher pressure, the boiling point rises to a higher temperature. This means it will take more heat to make the water change phase at a higher pressure. Note that the boiling point will also be different if your substance is not pure water. For example, if there is salt or other minerals dissolved in the water, the boiling point will change. If we are heating up pure water and it doesn't reach 212 degrees Fahrenheit, the water will not change to vapor. For example, if we heat up the water to 180 degrees Fahrenheit, the water becomes hot but it does not bubble. Bubbling is an indication of changing from liquid to vapor. If the temperature of the water is close to 212 degrees Fahrenheit, you will see a few bubbles forming. This is because the bottom of the pan is in direct contact with the heat source, so it gets hot faster than the top of the pot. So the bubbles indicate that some molecules on the bottom have reached 212 degrees Fahrenheit and are changing phase. The condensation point is the temperature at which vapor turns to liquid. Note that the condensation point is the same as the boiling point. That means if you have pure water vapor at 250 degrees Fahrenheit and you let it cool, the water vapor will condense into liquid at 212 degrees Fahrenheit. Both the boiling point and condensation point are properties of pure substances only. We will discuss the boiling temperature for mixtures when we discuss refrigerant blends.
The boiling point is the temperature at which substance turns from liquid to vapor. Okay, the turning boiling point is the temperature substance turns from liquid to vapor. Yeah, true. The boiling point for most refrigerant is 212 Fahrenheit. This is
As
false.
temperature of a substance is decreased, the substance also changes state. For our purposes, the state change we are most concerned with is condensation. In the video, ice cubes are placed on top of the cup to remove heat from air under the cup. Condensation occurs when temperature is decreased, changing vapor to liquid. To reiterate, you need to remove heat from a substance to change state from vapor to liquid. A decreasing temperature is the opposite of boiling. A decreasing temperature means a slower average speed of the substance. As molecules slow down, they start to form bonds with other molecules around them, forming a liquid. We see this commonly on windows on a cold day. Outside air is much colder than inside air, making the windows also cold. Since the cold window is in contact with warm indoor air, heat transfers from water vapor in the air to the cold windows, condensing the water vapor to liquid droplets.
Condensation happens when a gas or vapor cools down and becomes liquid. Yeah. If we decrease the pressure of substance, its boiling point decrease. Yeah. You are boiling a pot of water with the lid on. As the water heats up and starts to boil, you notice that drops of water form on the bottom of the pot. This is an example of condensation. Now, yeah, let's read it again. You are boiling a pot of water with a lid on it. As the water heats up and starts to boil, you notice that drops of water form on the bottom of the pot lid. Yeah, this is an example of condensation.
In this chapter, we reviewed the three
Yeah.
main states of
Okay.
matter. We also discussed boiling and condensation. Understanding how increasing and decreasing temperature is related to the different states of matter will help us understand how HVAC systems can provide cooling.
Okay, so for refrigeration cycle, we finish essential chemistry and physical state of matter. Let's go to the next one, this refrigeration cycle overview.
In this module, we will go over the basic concepts behind the refrigeration cycle and discuss how it powers your air conditioning and refrigerator.
In your daily life, you are likely surrounded by comforts made possible by the refrigeration cycle, especially during the hot summer months. The refrigeration cycle is what powers your air conditioning unit and, on a smaller scale, your refrigerator.
Air conditioners pull off the seemingly magical feat of making the air inside a home, car, or shopping mall deliciously chilly. Air conditioning, as well as refrigeration, which is the same thing just in a slightly smaller box, relies on the laws of physical chemistry. And PChem tells us that as a liquid evaporates into a gas, it absorbs heat. The molecules in a liquid are held together by weak intermolecular interactions. Not quite chemical bonds, just enough passing attraction to keep them from flying apart. Some of the molecules absorb enough heat energy, in other words, they get moving fast enough, to overcome these intermolecular attractions, escape, and take gaseous form. That's the reason you feel chilly getting out of the shower, and why we sweat to stay cool. The water has to absorb heat to evaporate, and it carries that heat away from you. An air conditioner's basic job then is to use a fluid called a refrigerant that constantly changes from a liquid to a gas and back to a liquid again to move heat from one place, like your sweaty bedroom, to another, outside, where it's already hot and miserable anyway, so who cares? Here's a admittedly very schematicified version of how most AC units work. The liquid refrigerant flows through a series of coils exposed to the air in your home. The refrigerant has a low boiling point, so the heat from the interior air is enough to make it turn into a gas, which means there's now more heat in the refrigerant and less in the air. A fan blows that colder air into your room, or straight into your face. We're not judging. So now your AC has to do two things. Dump the heat absorbed by the refrigerant outside, and two, it has to condense the refrigerant back into a liquid so it can be used again. And to do those things, it uses a compressor to ramp up the pressure on the gaseous refrigerant, so much that it can condense into a liquid again, even though it's at the warmer outside temperature. As it condenses, the refrigerant loses heat to the air around it, which another fan blows outside where it's already all sticky anyway. Which is a neat trick, boiling something at a low temperature and then condensing it at a high one. Nothing in thermodynamics is free, and the compressor needs energy to do the work of compressing the refrigerant, which may explain your power bill in July. After the refrigerant condenses, the air conditioner backs off the pressure with an expansion valve so that the refrigerant can boil at the lower temperature again, which it does, in a loop, over and over, until your home reaches the temperature you set the thermostat to, or your housemates complain and switch it off because what are you, a polar bear or something? Jeez. While the refrigerant could be practically any substance, there are some chemicals that do the job better than others, and these refrigerants have a checkered history. A refrigerant needs to have a pretty low boiling point, and one that can be adjusted to where you want it by changing the pressure on it. It should also be pretty good at conducting heat and be able to absorb a lot of heat as it boils. And then it needs to be cheap, widely available, and as non-flammable and non-toxic as possible. That all kinda narrows your choices of chemical. Scientists thought they'd found the perfect refrigerant with Freon, which is the trade name of a group of chemicals called chlorofluorocarbons. But CFCs are actual murder to the ozone layer. They've been largely replaced with hydrofluorocarbons, or HFCs. HFCs don't damage the ozone layer, which is good, but they have a different problem. They're greenhouse gases. So the search is on to phase out HFCs too. Some alternatives? Simple hydrocarbons like these have been approved in the USA. Hydrofluoroolefins like this one are less rough on the climate than HFCs, but also more expensive. The most surprising potential replacement is CO2. CO2 totally works as a refrigerant, and even though it's the literal poster child for greenhouse gases, it's also way less potent than HFCs. Whatever we use in the future, it doesn't seem likely that we'll give up on AC altogether. Not in a scorching summer like this one. Pass the popsicle.
As mentioned in the video, air conditioning works by absorbing heat from your indoor air and ejecting it outdoors. It does this by passing a refrigerant with a low boiling point through a series of coils that come in contact with warm indoor air. Boiling point is the temperature at which a liquid turns to vapor. In the refrigeration cycle, we use refrigerants with boiling points lower than your indoor temperature on a hot day. This is so that your indoor air is warm enough to make the refrigerant boil. The most commonly used refrigeration system is called the direct expansion vapor compression system. This type of system is found in both your air conditioner and refrigerator. In direct expansion systems, the cooling effect comes from the expansion of a liquid to a vapor. Think about how water turns into steam. As it evaporates, the hot steam rises and expands, filling a much bigger area than the water in the pot. This is the expansion exhibited by liquids when they turn to vapor. As the refrigerant boils, it changes state from liquid to vapor through a process called vaporization. During vaporization, or boiling, continuous heat is needed until all the liquid has changed state to vapor. It is important that the liquid stays above its boiling point throughout the process of vaporization. Think about boiling a pot of water. You apply heat to it by turning on the stove, which increases the temperature of the water. Once the water reaches its boiling point, it starts to bubble and turn into steam, which leaves the pot and dissipates into the air. If you keep the stove on, you are continuously applying heat to water that is already at its boiling temperature. More and more water molecules turn to steam or water vapor. If the stove is left on, the water in the pot will continue to boil until it all eventually turns to vapor. You've probably seen this if you've accidentally left the stove on too long. Either the pot completely dries up or there is much less water than before. The amount of water in the pot decreases as it vaporizes. If you turned off the stove after the water starts to boil, the water will stop boiling and remain in the pot. This demonstrates that you need to continuously apply heat in order for all of the water to become vapor. In the refrigeration cycle, it is refrigerant that boils, not water. Also, instead of a flame or electrical heat source, it is warm indoor air that provides the heat that causes refrigerant to boil. This process draws heat away from the indoor air, making it cooler and more refreshing. To reiterate, it is the boiling or vaporization of refrigerant using the heat from warm indoor air that creates the cooling effect in a refrigeration system. We learned earlier that vaporization is the process through which a substance changes from a liquid to a vapor. The refrigerant boils constantly as it moves through the system, transferring heat from inside the house to outside the house.
Your air conditioning works by introducing cold air into your house. True. Okay, here in the United States, throwing air outside, but in the countries that they are hot climates, they are this one will be correct, but here in the United States it will be false. Refrigerant absorbs heat from your indoor air in order to select all that apply in order to change state from vapor to liquid, change state from liquid to vapor, change state from vapor to liquid, make your house cooler, okay, absorbs heat from your indoor air, okay, so it will make it, oh my god, there is something wrong, change the state, yeah, from vapor to liquid, okay, this number one, evaporate it into the air, incorrect, it will be B and C are correct. This means it will change the state from absorbs heat from your hot indoor air to make your house cooler, yeah, as well as change the state from liquid
refrigeration
to
cycle is
vapor.
what creates the cooling effect in your air conditioning system
Okay.
or refrigerator. In an air conditioning system, for example, refrigerant absorbs heat from warm indoor air and begins to boil, changing state from liquid to vapor. This process cools the indoor air and dispenses the heat outside the house. This is why it is important for refrigerants to have a low boiling point. In the next module, we'll go into more detail about the components of the refrigeration cycle and what happens in each component.
Yeah, so we finish the refrigeration cycle overview. We will go to the next part, this refrigeration cycle components.
In this module, we will discuss the individual components of the refrigeration cycle, their function, and what happens to refrigerant in each component.
Aside from the refrigerant flowing through the system, the four key components of a refrigeration cycle are evaporator, compressor, condenser, and metering device, also known as a thermal expansion valve, TXV.
We're taking a look at a refrigerant piping diagram here to show you the basic components, and we'll also look at it in the lab as well to show you what they physically look like in real life. So up here on the top left hand of my screen, you see I have a condensing unit outside and I have a fan coil with an evaporator coil on the inside. It could easily be a furnace with an evaporator coil as well. So inside the home or inside the building, the job of that coil is to absorb heat from the house, transfer that heat through the piping, and then dump that heat into your yard. Right, so that's how we're actually doing stuff. We're not actually making your house cold. I mean, we are, but we're really removing the heat from a house and dumping it outside into your yard. Now, it's kind of weird because heat always goes from hot to cold. So we're taking it from your cool house and putting it into your hot yard. It's kind of weird. So we got to play a little bit games with the pressures to make that happen. Pressure, temperature, and volume are inherently connected to one another. And if I have a fixed volume like I have on a refrigerant piping system, and I change the pressure of something, the temperature must change. There's no ifs, ands, buts about it. So we got those things work together no matter what. So when I look at the piping diagram here, I have four major components on a refrigeration cycle. I have my condenser coil, which for a typical residential split system, that's out in your yard. It's part of your condensing unit. I have a compressor, which is also part of your condensing unit. Then inside the building, I have my evaporator coil, and my TXV. And the TXV and evaporator coil are typically in one assembly as well. So visually it looks like I have two things, but really there's four major components of the refrigeration cycle. The condenser coil and the evaporator coil are doing opposite jobs of each other, and the TXV and the compressor are doing opposite jobs of each other. Condenser coils absorb heat, condenser coils reject heat, evaporator coils absorb the heat. Compressors compress the refrigerant, expansion valves or metering devices allow that refrigerant to go back to a lower pressure. So on the left-hand side of my dotted line, I have high pressure. On the right-hand side, I have low pressure. So the TXV and the compressor divide those pressure barriers. So let's just follow a refrigerant molecule around the loop here, right? So let's just start with the evaporator. So I have a refrigerant molecule sitting there in the evaporator. He is absorbing heat from the air of your house running through your furnace and evaporator coil assembly. He's absorbing that heat, which is raising the temperature of the refrigerant. It's increasing it up as he absorbs that heat. And then that refrigerant is going into the compressor, where the compressor's job is to compress the refrigerant to raise the pressure even more. And because I have a fixed volume, when I raise the pressure, the temperature goes up as well. So you can see in our example here, I'm starting out with 40 degrees leaving the evaporator, or in the evaporator coil, and I'm ending up with 120 degrees in the condenser coil because I raised the pressure from 120 up to 420. So raising that pressure raised the temperature. So now that that compressor sends that refrigerant to the condenser coil, it's 120 degrees, but my yard's only 90 degrees. So now I can transfer heat from the coil to the yard, to the air outside, because it's going from 120 to 90. So there's a temperature difference there to move the heat. Then inside that condenser coil, as I'm removing the heat from the condenser coil and sending it to the outdoor air, that is lowering the temperature, which eventually causes the refrigerant to condense, which is why we call it a condenser coil. The evaporative and condenser words go in relation to what's happening with the refrigerant, not what's going on with your air. So it condenses the refrigerant back to a liquid, which is why we call this the liquid line, and that travels over to the TXV. TXV stands for thermal expansion valve. It is a metering type device. Older systems would have had fixed orifices or pistons or something like that. Nowadays, almost everything has a TXV. His job is to meter the refrigerant and control it as it enters into the evaporator, as well as to change the pressure from high back down to low, because he's the opposite of the compressor. And then that goes back into the evaporator coil with a lower pressure, where it can now begin absorbing heat again. That's kind of our basic refrigeration cycle here. You notice we have some of the pipes labeled on here. The hot gas line between the compressor and the condenser, you don't normally see that. That is internal to a condensing unit. because the condensing unit, if you recall, has the condenser coil and the compressor all in one. So you don't see that hot gas line typically. The liquid line and the suction line are the two lines that you see going from outdoors back indoors to the inside the building. And then the line between the TXV and the evaporator is typically all in the evaporator coil as well, so you don't see that unless you take the cover off. Here we are in the lab. We have a furnace with an evaporator coil on top of it. Air from the building or the home is coming through the furnace, because that's where the blower motor is, running through the evaporator coil, where the evaporator coil can absorb heat from the building, and then the air gets cooled down, obviously, when it gives up its heat and gets ducted out to the supply. But that heat goes into the evaporator coil, and then that heat will make its way through the suction line, in our case up over the ceiling in the lab here. It'll come down into our condensing unit. And then as it comes in our condensing unit, the suction line comes through here, goes into the compressor, where the compressor increases its pressure and hence increases its temperature. Then it leaves the compressor on the hot gas line. If we follow that pipe all the way around, that hot gas line goes into the condenser coil, where it can use all this surface area to reject the heat to the outdoors. And then when it comes back out of the condenser coil and goes into the liquid line, and then the liquid line will make its way back through the piping system, back into the indoor side of the building. Now our liquid line will come in this way. It'll go into our TXV, which is a little tough to see in here. And then the TXV's job, once again, is to lower the pressure and hence lower the temperature. So we have cool refrigerant entering to the evaporator coil, where it's now cool enough where it can absorb more heat from the air. And then that cycle will repeat itself, hence why we call it the refrigeration cycle.
Let's now look at each of the components individually, starting with the evaporator.
In my basic refrigeration description, I talk about the evaporator as being the heat absorber. It pulls in heat, and that's really what we're trying to do when we're attempting to cool something, is we make the evaporator coil of a lower temperature than either the room or the box, the air going over it, so that way heat goes out of that room or that refrigerator box or that freezer, and the heat is attracted into that evaporator coil. And often for most of the typical basic systems we're working on, we're just flowing air over the evaporator coil, over those fins on that evaporator coil, and then as it passes across that metal and the refrigerant moves through, it's absorbing heat through the metal into the refrigerant. The fins on those coils that you'll often see act as additional surface area to help give it a little bit more contact time, so that as that air is passing over, it has more contact time on the metal, so that way that refrigerant inside that evaporator coil can absorb heat.
The evaporator is located inside the home. This is where refrigerant absorbs heat from indoor air, changing from liquid to vapor. As seen in this video, the coils increase the surface area that the warm indoor air contacts when it passes over the evaporator. The increased surface area allows for more heat to be transferred to the refrigerant inside the coils. We also see in this schematic that as refrigerant in the evaporator coils absorb heat, it changes state from liquid to vapor. It gets heated up past its boiling point, which makes it superheated vapor by the time it leaves the evaporator. This change into a superheated vapor state is indicated by the color change of the coils from blue, liquid, to red and yellow, vapor. Vapor refrigerant is let out from the evaporator to the next component, the compressor.
When the refrigerant enters the evaporator, what state it will be? It will be vapor. Sorry, liquid. Refrigerant enters the evaporator as liquid, where it absorbs heat from air to change the state of vapor. When the refrigerant exits the evaporator, okay, it will come liquid. It will be vapor also. It will come vapor. It will enter as a liquid and going out as a vapor. After evaporator, which component does the refrigerant go to next? Evaporator, it will go to compressor.
Up here. And so let's talk about this in metaphor. So imagine the room that you're in right now. Whatever room you're in, it's got the four walls that surround you, and then it's got the ceiling. And now imagine that this room that you're in, that you're occupying, is full of ping pong balls. And these ping pong balls, they bounce around perpetually. They're always bouncing. And these ping pong balls, they signify molecules. And so the energy that these molecules contain that causes them to bounce around, that's heat. But the speed that these molecules or ping pong balls are moving at, that is temperature. In fact, temperature literally is average molecular velocity. I talk about this a lot on the podcast and in these videos. So when you feel something as hot, what you're really feeling is you're feeling those molecules bouncing around or vibrating very fast in that thing that you touch. When you touch that hot stove, you're literally saying you're coming into contact with molecules that are bouncing around really fast, and that causes the molecules in your fingertips to bounce around really fast, which can be quite uncomfortable, cause burns, right? So when we experience temperature, we are literally experiencing the molecular velocity of whatever substance. So this, this little bottle of water here that we've got, the temperature that I feel of this water, my fingers are experiencing through conductance the molecular velocity or the speed that the molecules are moving. So back to our room. You have this room, it's full of these ping pong balls that are bouncing. Amount of overall energy that they contain is the heat. The speed that they're moving is the temperature, and the ping pong balls themselves are the molecules. And in this case, it's refrigerant. So now imagine that one of these walls begins moving in. So imagine it's sort of like the scene from, Star Wars, where the room is getting smaller and smaller and they start to be crushed, right? And so as this wall moves in, what happens to these ping pong balls? Do they speed up or do they slow down? This wall, as it moves in, is working against the force of those balls bouncing off of it. And as it does that, the speed of those balls, as they bounce against the wall and against each other, start to increase. The molecular velocity begins to increase of these ping pong balls. And so what happens is the temperature increases, because again, remember, molecular velocity is temperature, the same thing. And so that's what's happening inside of a compressor. And if you think of this scroll compressor behind my shoulder here, it goes in as vapor. In fact, how it really works inside of a compressor is that suction line, the refrigerant drops into a refrigerant-cooled compressor's shell. It cools the compressor, kind of mixes with the oil, and then it's pumped out into the head where then it's discharged. And so there is some heat added from the compressor itself to cool it, from the windings and from the different parts inside there with the friction, the bearings and all that. There is some heat generated there, but really the bulk of that temperature change that we're seeing from, say, on average, on an air conditioner, and an average suction line temperature would be, say, 50 degrees. And then coming out of the compressor, you'll commonly see about 165, 170 degrees. And so that's a significant difference in temperature, say 120, 130 degree differential. And that differential is representative primarily of that heat of compression, which is, as the compression chamber gets smaller and smaller, the molecules in there are bouncing faster and faster. Just like if you imagine that room with the wall moving in, the ping pong balls are moving faster and faster. And so are you changing the amount of heat? The answer is yes, you are, because there is work that's being done against the forces. But primarily what you're doing is by compacting them into a smaller space, you're taking the heat that was already in that suction gas that already came from inside the house. You're packing those molecules closer together, and you're revealing that heat in the form of temperature. So a way of thinking about this is when you add pressure, you increase temperature. This is part of the gas laws. When you add pressure, you increase temperature. And by increasing temperature, now we can get that heat back out of the refrigerant in the condenser. So what does the compressor do? Well, it compresses, obviously. Like we said, it causes the refrigerant to occupy a smaller space. In doing so, that increases the temperature. And by increasing the temperature of that suction gas, now we can get the heat back out, because hot goes to cold. So that's what that compressor does. In addition to that, like we said, with refrigerant-cooled compressors, which is the majority of what you work on if you work in air conditioning or small refrigeration, that suction gas also does serve to cool that compressor. But primarily what's happening is you have that heat coming down that suction line at a low temperature, goes into that room that then squeezes those ping pong balls together. The molecular velocity greatly increases, and now we can run it into the condenser where we can remove the heat from it again, and they slow back down again, and it can then turn into a liquid. So that's just a basic look, and that's one of my favorite metaphors to explain what's going on into a compressor, because when you sit in that room and you imagine those ping pong balls bouncing around, and that's the refrigerant molecules, it just gives you kind of a picture, a way to envision what's going on. And just remember, in that metaphor, the ping pong balls are the refrigerant molecules bouncing around, and the speed that they're moving or the velocity that equals.
After the refrigerant is boiled to a vapor in the evaporator, it is sent through the suction line to the compressor. The compressor's job is to increase the pressure of the refrigerant. In our essential chemistry module, we observe that as pressure increases, temperature increases too. This is exactly what the compressor does: increase refrigerant temperature by increasing the pressure. We can see a visual representation of that in this video. Refrigerant is then sent from the compressor to the next component, the condenser.
When the refrigerant enters the compressor, what is the state is supercooled vapor, supercooled liquid, superheated vapor, superheated liquid. As we know, it is increased pressure and temperature, so I think it is superheated liquid. Superheated vapor. Superheated vapor. Okay, because it's enter as vapor and it will be compressed. What is the compressor job? Is to cool the superheated vapor, is to increase the temperature, is to increase pressure. Yeah. The vapor leaving the compressor is lower in pressure than vapor entering the compressor? No. The job of the compressor is to increase pressure. Yeah. Does the refrigerant change state in the compressor? Does the refrigerant change state in the compressor? No, not change the state. It doesn't change the state. Yeah.
Saturation. So those are the three things that happen inside that condenser, but how do they do it? Well, the condenser has to reject heat. That's its job. It's the heat rejector. So it has to reject heat to something. And in this case, it's generally air. And your typical air conditioner at your house, a split system package unit, window unit, whatever, it's generally the air. But it can also be water. It could be glycol. It could be a lot of different substances. It could be another refrigerant that's used. But the goal is to get that heat out of that refrigerant and to something else. Now, that something else that is rejecting its heat to, by its very nature, has to be a lower temperature. As an example, we'll use a typical residential split system. So let's say you have a condensing temperature of 110 degrees, we'll say, and you have an outdoor temperature of 90 degrees. You'll notice there's a 20-degree difference. That outdoor temperature has to be lower than that condensing temperature in order for heat to come out of the refrigerant in the condenser and to be rejected into the air. First rule, hot goes to cold, right? You have to reject heat from the condenser to something that is a lower temperature than the condenser. So when you look at that condensing temperature, and we do that by looking at a gauge, and it tells us what that condensing temperature is, by its very nature, it must be higher than the medium that we are rejecting to. So whereas air is not the best thing to reject heat to, water is better. So there's differentials might vary, but regardless, no matter what we're rejecting to, the temperature rejecting to must be lower than the temperature of the refrigerant in the condenser. That's that condensing temperature. It's also useful to know that most condensers are piped, especially the air-cooled types that we work on generally. They're piped so that way the refrigerant starts in the top. So it comes out of the discharge line from the compressor, goes into the top of the condenser, and then works its way down until it becomes fully liquid at the bottom, or subcooled. Again, subcooled is temperature below that condensing temperature. So that's mostly it. Condensers can reject heat to a lot of different types of mediums, but they are all heat rejectors, and they go through the three phases. They all have to. The desuperheating phase that brings it to the condensing temperature, which is that first little bit in the top. And then you have that condensing phase, which is through the bulk of the condenser. And then at the end, that's when you have the subcooling phase, which is the drop below the saturation temperature. You can only have subcool once the refrigerant is fully liquid. You can only have superheat if it is fully vapor, and that condensing temperature segment is all there in the middle. So it's like watching a boiling pot of water, but in reverse. It's changing from liquid to vapor instead of vapor to liquid. That's your condenser, the heat rejector.
Refrigerant is sent from the compressor to the condenser via the hot gas line, since refrigerant exits the compressor as a hot, high-pressure gas. As seen in the video, the condenser is housed in the same unit as the compressor. The condenser is located outside the building so that the coils containing the refrigerant can come into contact with outdoor air. Since the compressor increased the temperature of the refrigerant is now hotter than the outside air. This causes heat to transfer from the refrigerant in the condenser coil to the outdoor air, cooling the refrigerant. In this video, we see blue arrows going into the unit. These represent cooler outdoor air flowing over the condenser coils. It doesn't necessarily mean that the outdoor air is cool. It's just at a lower temperature than the compressed refrigerant inside the coils. As outdoor air passes over the condenser coils, it absorbs heat. Air that is exiting the unit is hotter after absorbing heat from the refrigerant in the coils. This is why the arrows leaving the unit are colored red. Think of a steaming mug of coffee. Because it is hotter than the surrounding air, heat will transfer from the coffee to its surroundings. You can feel the heat transfer to you when you wrap your hands around the mug. Remember, heat moves from hotter to cooler mediums, which is basically what happens in condenser coils. As the temperature decreases in a hot vapor, it will condense. Condensation is the process through which vapor changes from vapor to liquid. We commonly see condensation on windows on cold days. Heat transfers from the vapor to the cold windows, condensing it to liquid droplets. In the condenser, heat transfers from the refrigerant to outside air. Refrigerant inside the condenser cools until it changes state from vapor to liquid. The refrigerant is then sent from the condenser to the next component, the metering device or thermal expansion valve, TXV.
What is the condenser job? To cool the high pressure vapor, yeah, to cool the high pressure vapor. In the condenser, the refrigerant changes state, from vapor to liquid. The condenser does an opposite job, of which component
is a type of metering
is
device, and the
evaporated.
purpose of the metering device is to act as a pressure dropper. It's there to create a pressure drop. And so it separates the high side and the low side of the system. If you look at the basic refrigerant circuit, you'll notice that the compressor and the metering device kind of split that circuit in two, where the compressor is the pressure increaser, and then the metering device is the pressure dropper before it goes into the evaporator coil. So think of it in this way. The compressor has to pressurize the refrigerant before it enters the condenser in order to get the heat out, and the metering device has to drop the pressure before it goes into the evaporator coil to get the heat in, because when you drop pressure, you drop temperature. When you increase pressure, you increase temperature. And you have to manipulate temperature in order to get heat in and out of things, which is what we're doing with the refrigeration circuit, is we're getting heat in and out of things. So there are several different types of metering devices. You have capillary tubes, you have pistons, you have TXVs, and you have electronic expansion valves. There's a few other more exotic types of metering devices that you'll read about in books, and we're not going to talk about those here. Automatic expansion valves, high side, low side float, systems like that. But we're going to focus on these four and just talk a little bit about what the general purpose of the metering device is. So we know it's a pressure dropper. How does it do it? Well, it drops pressure by basically creating a small passageway that the refrigerant has to go through. So pressure is built up on the inlet side, and then on the outlet side there is a drop because it goes through a very small area, and then it opens up into a larger volume. So when we think about the relationship between pressure, volume, and mass, we know that if you increase volume, then you decrease pressure. And what we're doing is we're increasing volume because it goes into an evaporator coil out of a liquid line. A liquid line is a smaller line. It goes into this larger volume of space into an evaporator coil, so there's an increase in volume. But we're also controlling the amount of flow moving in, so we're controlling how much pressure is able to make it into that evaporator coil. All that said, we end up seeing a pretty significant pressure drop across that metering device. That's what it
Refrigerant enters the metering device from the condenser via the liquid line, since refrigerant has cooled enough to condense into a liquid. The metering device decreases the pressure of the refrigerant so that it can be sent back to the evaporator. There, it can repeat the cycle of absorbing heat from warm indoor air.
What is the function of the metering device?
In conclusion,
To
there are
decrease
four
pressure
main components to the
to
refrigeration
decrease pressure.
cycle: the evaporator, compressor, condenser, and metering device or thermal expansion valve, TXV. The main function of the refrigeration cycle is to absorb heat from warm indoor air and dispel it outdoors. Different refrigerants can be used in the refrigeration cycle. In the next module, we will discuss the different types of refrigerants that can be used.
Yeah, so this one in refrigeration cycle we finish essential chemistry and physical state of matter and the refrigeration cycle overview and the refrigeration cycle components. This is the last one is state and pressure changes.
In this module, we show how refrigerant state and pressure change through each piece of refrigeration equipment.
Let's look at a video to get a brief summary of the state changes within the different components of the refrigeration cycle.
In this animation, the color of the arrows indicate the condition of the refrigerant. The red arrow means that it is in a vapor state, whereas the blue arrow means that it is in a liquid state. So as the refrigerant comes out of the compressor, it is in a superheated state, in vapor state, and so we see these red arrows going through the condenser where the refrigerant condenses into a liquid. As the refrigerant vapors condense into liquid, heat is discharged to the surroundings, as we see here. And then that liquid goes through the expansion valve, where it is essentially changing from a high pressure side to low pressure side. So as it goes through the expansion valve, most of the refrigerant stays in the liquid state, but some of it does turn into a vapor state. So that mixture of liquid and vapor goes through the evaporator, where as the heat is extracted from the surroundings, the refrigerant state changes all the way from liquid to vapor. And then we have a refrigerant in the vapor state going into the compressor.
In the evaporator, refrigerant absorbs heat from the indoor air. This heat increases the temperature of the refrigerant until it boils. Heat from the indoor air raises the refrigerant's temperature past its boiling point, making it a superheated vapor. Refrigerant changes from liquid to vapor here, so the evaporator contains both liquid and vapor. In the compressor, refrigerant is fully vapor. Because the compressor increases the pressure of the refrigerant vapor, it increases in temperature but stays as a vapor. Refrigerant enters the condenser as a high-pressure, high-temperature vapor. It cools as the coils come in contact with outside air, turning from vapor into liquid. So in the condenser, there is both vapor and liquid. In the metering device, refrigerant is fully liquid as it changes from high to low pressure liquid. It passes back to the evaporator and repeats the process. This chart summarizes the states of refrigerant in each component of the refrigeration cycle.
When the refrigerant exits the evaporator, what state in it? it will be vapor, okay, with high pressure. Vapor, okay, with low pressure, not compressed, with low pressure. What is the state refrigerant when it enters the condenser? It will enter the condenser, okay, the condenser, it will enter as a vapor, okay, it's high pressure vapor, and yeah, high pressure vapor. When refrigerant enters the metering device, what is the state of refrigerant enters the metering device? It is high pressure, okay, it is welcome high pressure, it affects the condenser, it will become high pressure vapor, sorry, high pressure liquid, high pressure liquid. When refrigerant exits the metering device,
Changing
what is the
pressure plays an
state?
important part in the
It will be
refrigeration cycle,
low
as was
pressure
discussed in the
liquid.
videos. Changing pressure allows us to move heat from inside the house to outside. We can separate the components of the refrigeration cycle into a high-pressure side and a low-pressure side. On the high-pressure side, we have the compressor and the condenser. The high pressure allows for heat to be dispelled from the system to the outside air. An increase in pressure causes an increase in temperature. The higher temperature in the refrigerant allows for heat to be released from the system to the outside air. On the low pressure side, we have the metering device and the evaporator. The metering device is useful for controlling conditions within the evaporator so that it can absorb heat from your indoor air. As mentioned in previous videos, the following components change the pressure of the refrigerant. Compressor increases pressure. Metering device decreases pressure. Here, we have added the pressure of the refrigerant in each component to the chart we created before.
Which component change the refrigerant pressure? The metering device and the compressor. They changed the pressure. Yeah. Which component are on the high pressure side? Which components are on the high pressure side? Okay, the high pressure side, it will come the condenser and the evaporator. No, the condenser and
In this module,
compressor.
we discussed how state and pressure changes happen in different components of
Condenser
the
and
refrigeration
compressor.
cycle, and how each change contributes to cooling.
Okay, so we finished the refrigeration cycle. Let's take the quiz. Okay, let's attempt the quiz. In the quiz here we have 29 questions. Okay, let's start. What is the next component the refrigerant flow to after passing through the evaporator? Okay, it will come the evaporator. Okay, evaporator, and after this evaporator, it will come after will be the compressor, I think. As the temperature of liquid increased, what phase does it turn it into? Assume constant pressure. Temperature of liquid increase, it will come to vapor. Okay. Does the refrigerant change state in the compressor? No, it doesn't change the state. When pressure is increased on a liquid while keeping the temperature is constant, what state can substance change to? It can change to solid. The refrigerant absorbs heat from your indoor air in order to make your house hotter, change state from liquid to vapor, make your house cooler, yeah? Change the state from liquid to vapor. Which component has the opposite function of the condenser? The evaporator. What is the compressor job to increase the pressure? What is the condenser job? Condenser job to cool high pressure vapor. What is the function of meter device? Decrease pressure. What is the state of the refrigerant when it enters the condenser? When enters the condenser, it will be vapor. Vapor, high pressure vapor. When the refrigerant enters the meter device, what is the state? It will enter liquid, high pressure liquid. When refrigerant exits the meter, what it will be? Low pressure liquid. When refrigerant enters the compressor, it will be low pressure liquid also. Liquid, super cooled. Liquid, yeah. Liquid, but in low pressure. Super cooled. When the refrigerant enters the evaporator, what is the state is? Refrigerant enters liquid. When the refrigerant exits of the refrigerant, the state of vapor. What is the state of the refrigerant when it exits of the evaporator with its vapor? Okay. Vapor, low pressure vapor. Which of the following components are associated with the high pressure side of the refrigerant? High pressure, it will be compressor, okay, and condenser. What component changes the refrigerant pressure? Changes the pressure of the compressor and the condenser. Sorry, no. Metering device, okay, and the compressor. Which of the following states has a high temperature? A high temperature. Has the highest temperature? The vapor. Boiling requires the addition of heat. Yeah. Condensation happens when a gas or vapor cool down and become liquid. Yeah. For the same substance at the same temperature, The average speed of molecules in vapor is the same as the average speed of molecule in liquid. False. If we decrease the pressure of substance, its boiling point decrease. Yeah. In the condenser, the refrigerant change state. Condenser. In the condenser, yeah, change the state. The boiling point is the temperature at which substance change from liquid state to vapor or gas. Yeah, the boiling point of most refrigerant is 212 Fahrenheit. False. The vapor leaving the compressor in lower in pressure. Okay, in lower in pressure. Than vapor entering the compressor. No. You are boiling a pot of water with a lid on. As the water heats up and started to boil, you notice that drop of water from on the bottom of the pot liquid. This example of condensation. True. Yeah, I remember this question. Your air conditioning works by added cold air into your house. Works by adding cold air into your house. True. Yeah. Let's see the result. Okay, we answered all. Let's submit and see if there is something. We have 8.97. Okay. Okay, that's correct. Correct one. Let's check the wrong question so we can learn from our mistakes. This one. The refrigerant enters the compressor from evaporator. Enter the compressor in which state? Okay, enter the compressor from the evaporator. It is superheat. Not super cool, superheat liquid. Superheat vapor state. Okay, let's go down. Go down. For the same substance at the same temperature, the average speed, same substance, same temperature, the average speed of molecule in vapor is the same as average speed in liquid. Oh, it's true. So the average speed in case of same temperature for liquid, it's the same as vapor of the same material. This one also, your air condition is worked by adding cold, and you know is removing heat but not adding cold. Okay, now let's finish review. So we finish the refrigeration cycle. Okay, we finish the refrigeration cycle. We finish essential chemistry and physical states of matter and refrigeration cycle overview, refrigeration cycle components and state and pressure change. We finish also the quiz.